Another day, another chance to prove ourselves to the LeetCode gods that we're worthy of favor, that we're worthy, that we're warriors. Honestly, we're the LeetCode warriors. It's day 30, 30 days of, trying hard at something. I think it's important to be able to, see how far you can go at something. And, maybe not for most people, but this challenge itself, I think has pushed me to a new height, to be honest. I mean, there's something to say about being able to withstand stress tolerance. I mean, many people who have done very, very cool things. I mean, one of their hallmarks is their ability to handle stress, right? So I think that's pretty cool. I'm not saying that this is the most stressful thing in the world, but I mean, let's be honest. If you're working at something, you're working at it, for example, you might work out an hour a day, maybe 2 hours a day. It's a completely different regimen or requirement or band or bound of consistency and challenge to be able to do, maybe a 5 or 6 hour, maybe 7 hour in the gym, right, over a long period of time. So I think that is pretty cool. Nowhere near that level. I think we're getting there, though. I mean, the amount of time I spend looking at these problems is ludicrous. I'm going to be honest. So that's pretty cool, but we'll see, how far that goes. That being said, the amount of problems done so far is pretty cool. I mean, just being able to cover, just to be able to look back, I think is one of the coolest things. I mean, when we started, right, I couldn't even do the simplest problem like two sum. I mean, now we're this many problems deep. That's just because we can visualize our progress here, but we've done so many more problems. But I think there's something cool about that. It's cool to be grateful about that. But either way, we're looking for dominance in the end anyway. We're looking to be able to dunk on all 2,400 problems, not even for a job. Just for the sake of conquest. I'm going to be honest. I just want to see if it can be done. Right? I'm sure there's someone else who's already done all these problems. That is besides the point. I mean, the journey that I'm aiming for with these problems, I just want to see if I'm capable of doing it. So if I could do all 2,400 problems, I would think that's pretty dope. But either way, if you're working on these 2,000 problems, join the Discord. It's the Hyperbolic Coding Chamber. Thousands upon thousands of people in there grinding. You could be number 2,000, but in reality, you'll be number 2. Okay? So we only have like 2 people in the Discord. That is irrelevant. But it's just a work in progress. It's just a cool place. We exchange some insider tips. I mean, some of these codes that you can type in, they instantly solve the problem for you. I mean, we also have some secret tips on how to drop a blank check, how to, maybe show your bank account by mistake to your interviewer and just be like, oh, no, I didn't mean that I could send half this money to you. But it's irrelevant. So that being said, there's a lot of progress made on the grind 75. Lot of problems done. I've only been doing it for a few days now, but it's been really cool to see just the progress. I mean, not being able to do one problem and being able to solve like 5 or 6 in a row is always a feel strong, man. That being said, I was absolutely fried by longest palindrome because this problem is actually the hardest problem on LeetCode confirmed. You want to avoid this problem at all costs. It is unsolvable. It says, right, 300K submitted, actually false. This is actually a fabricated number, right? No one's actually seen this question in an interview before because the interviewers can't solve this one. That being said, I think actually better, I practice the older problems that I do better off stream. I said stream, off recording, whatever. So I think on the days that we do practice, we're going to only do new problems. I think that's just where the money is. That's where the growth is. That's not to say I don't do old problems. I still most definitely do. I just don't do them on the recording. I just think the nature of the recording and what I'm aiming for and talking through it, right, it's just better for newer problems. That being said, right, we got stuck on the longest palindrome. Just going to go to reverse linked list, then to O1 matrix, and so on and so forth. Hour and a half on the clock as usual, but also 30 days. I mean, that is pretty cool. 30 days of there's something weird about calling it the grind, because it makes it seem like, I don't know, there's just something weird about calling it the grind. Something weird about calling it the grind. Okay, I have my finger on it. It kind of feels like what must be, I don't know how to explain it. Something just feels weird about calling it the grind. It kind of just feels like what must be done. So I don't know, there's something about the grind that makes, there's something about the connotation of that word that doesn't feel right. I mean, it is a grind, but I think most importantly, it's hard work. But I think there's a gratitude I have for hard work that, I don't know, there's just some contentment you get, at least I get from looking back and being like, oh my God, like, you did this and that. Like, that's pretty cool. Like, just being able to look back from 30 days, like, knowing that I did this at least for 30 days, already pretty dope, right? Already pretty dope. And I think things just be like that in general in life sometimes, just being able to look back, right? I think someone else said something like getting there, getting to where you're trying to go isn't like the funnest part, because you can't really feel it when you're there, right? I'm at day 30 now, and there's a lot of problems I couldn't even dream about solving that I can solve today that I couldn't solve a month ago. That being said, I mean, I can't even feel that difference. I can see it in my output, right? But the real difference, I think, is in like running that delta between where you are right now and the past, right? And when you look at that delta, it's like, good job, past me, good job. And I think, kind of like if you were driving, right? I mean, when you're driving 30 miles per hour and you speed up to 50 or 60 or 70 or whatever you get up to, I personally don't drive over 30 miles per hour because they're death machines. But if you're driving at 50 miles per hour, I mean, you can't even 50, 60. I mean, I've driven like 80 before, maybe once. But when you're going at 80, you can't even feel that you're going 80, right? And after a certain point, right, you get to 40, you can't even tell you're going 40, so you go to 50. You can't even tell you're going 50, so you go to 60, right? The only time you can actually tell you're going faster is during the acceleration. And so I think that's kind of what I'm trying to get at here. The time where you get that little dopamine rush in your brain, you know, it's really when you're starting to accelerate. And so that is pretty cool. I actually don't have a lot of reflections for 30 days. I think some of the biggest things, if I really had to talk about them, one of our longest preambles actually before we started programming, but just reflections on 30 days. It's been a lot longer than 30 days, to be honest. I think it's been almost 100 days. But the last 70 or so days, the throughput required, or the throttle, the torque, the gas required wasn't that high because I wasn't doing too much, maybe 20 minutes a day. But even that went a long way, right? Let me build the confidence to even go up to doing the time we do now. But that being said, reflections on 30 days, LeetCode, the grind, problem solving, intuition, building, memory bank, right? Practicing application, reflections. I feel like a lot of the intuitions we have about practice, application, performance are wrong. You know, I feel like Anders Ericsson talks a lot about this in a lot of his books. I mean, a lot of the intuitions people have about talent, skill, hard work are very flawed. I mean, even myself, I have those same intuitions that have been off. And I think it's just cool to see those changed and to be able to make them work. So I think 30-day reflection, I would say make sure to do old problems. I feel like the value in old problems is immense. I mean, it's just hard to quantify. It's kind of like when you go back to somewhere you haven't been in a long time. Like, nobody can relate, but let's say you went to high school. You are now 30 and you go back to your high school, right? Just stepping into the door, seeing the high school in real life, in person again, after that long, almost transports you, slingshots you back, you know, to when you were 12 years younger, and you have access to just so much context and connotation that you didn't have to just thinking about it, you know, in your bed at home, right? But I feel like just being able to have those associations automatically pop up in the context, you can already feel the difference, right? It's kind of like visiting a maze you used to get stuck in all the time, right? And then coming back to that particular maze and being like, oh, I could have just went this way and been fine. And I think that's really where the value is in old problems. But I think the most important thing with old problems is to make sure that you don't automatically just go right, right? I think it's important to think about exactly why going right is the right solution. I think it's through that mechanical action of actually solving the problem do we make like tangible progress in terms of building these like decision trees in our head. And yeah, maybe I can make another video about this another time. I really want to hot drop that what I learned for doing LeetCode for 30 days thing. Maybe I'll just cut this out, you know, or I'll make another video and rehash the topics. Gotta play the game. But yeah, I think I'll stop there. We are 1 hour and 30 minutes on the clock, and we need to get some things done. So we have the grind 75, and yeah, I'm just gonna jump into it. At the same time, make sure you join the Hyperbolic Coding Chamber Discord. There are thousands and thousands of people joining every day. At the same time, thank you if you've clicked the video, if you've thought about clicking the video but didn't click the video. Thank you if you drop an insult. Thank you if you drop a comment. Don't subscribe. Actually, report the channel. If you see this, if you get this far in the video, report the video. Report it for false advertising. Yeah. So that being said, I'm just gonna jump into the actual problems and do the thing. So let's do it. So we have 1 hour and 30 minutes here. Return, I was setting up a timer. We have 1 hour and 30 minutes, right? We're gonna try for 20 minutes on every problem, right? Just because honestly, that is the minimum required, right? So let's jump into it. And I'm gonna try and go slow, not go too fast, because when you go slow, you make mistakes. So let's do it. I'm starting it now. Start. And one more thing. I always forget, the final thing is I always kind of put my computer on focus mode just because I'm trying to focus, right? But obviously you gotta let important calls through and stuff like that. But it's just important, I'm just trying to stay focused, so have that turned on. So I'm just gonna jump into it. So we have reverse linked list. So given the head of a singly linked list, reverse the list and return the reversed list. So we have 1, 2, 3, 4, 5, and they want us to output 5, 4, 3, 2, 1. We have 1, 2, they want us to return 2, 1. If the list is empty, right, then the reversal of it is the nothing, right? If the list doesn't exist, then the reversal of it is also nothing, right? And our constraints, we know that the linked list could not exist, right? And so I'm thinking that maybe we could accomplish this with linear time and linear space with the stack, right? If we were to iterate through the linked list, on each iteration we could push the current node's value onto the stack, or to be honest, even the node itself onto the stack, then rewire it as we go through, right? And so if that's our goal, we could do it with linear time and linear space. So let's try that. We'll use a stack, right? We'll create a temporary variable which will point to head. We'll say while temp does not equal null, right? Because we want to iterate through it. And we're going to push each node onto the stack. We'll say stack.push temp. At the end, right, we'll know that we'll have the stacks in reverse order already ready to go, ready to be popped off, right? So from here, right, what we could do is we could iterate through the list again and simply overwrite the values of the linked list with the value stored in the stack, right? But we also have a reference to the value in the stack, so maybe we could do some pointer magic, right, in case we ever had to, you know, make this problem portable for other things that aren't strings or numbers or just holding a singular value, right? That being the case, we'd probably not want to keep copying it, so let's reuse the references. So we'd have the stacks in reverse order, and so we'd probably just want to say that we just have to reconnect them, right, in a new way. So we could say let head, right? And like we said, if the stack, I almost forgot, if the head that they're passing in doesn't exist, right, we want to return head, right? And so we'll say a new value, right? We'll just call it new head equals stack dot pop, right? So now we're having access to 5, and 5.next was initially null, right? So now all you have to do is say while the stack length is not equal 0, right? We're going to do stack. We're going to say new head dot next equals stack dot pop, and new. We're also going to want to keep a reference, right, to new head. We'll just set new head equals stack dot pop, and we'll just say temp equals new head just to reuse it, right? So we'll say temp dot next equals stack dot pop, and temp equals temp dot next. Then at the end we could return new head. So let's check if this makes sense. If the head does not exist, we're going to add values onto the stack. So let temp equals head, right? Const stack is just an array, right? Temp equals head, so we're at 1. Temp is not null, right? So we push 1 onto the stack. 2 isn't, and so this is exactly why it's important to look closer at our code. After we push temp on the stack, I'm going to say temp equals temp dot next. So say while temp is not null, 1 is not null, we push 1 onto the stack, we go to 2. 2 isn't null, we push 2 onto the stack, we go to 3. 3 isn't null, we push 3 onto the stack and go to 4. 4 isn't null, so we push 4 onto the stack, we go to 5. 5 isn't null, we push 5 onto the stack, we go next, right? And now temp is now null. We create a new, not really new head, but we grab the end or the new front of the list, right, with 5. And now that we have 5, we can pop it off. We'll say temp equals new head and keep a final reference of new head, which we can return. So temp equals 5, right? And while our stack still has elements in it, we're going to say, right, is our stack empty? No. So temp.next is going to equal stack.pop, which is 4, right? And then we're going to say temp equals temp.next. So now we're at 4. Is our stack empty? No. We're going to say temp.next equals stack.pop, right? And temp equals temp.next. Is our stack empty? No. Temp.next equals stack.pop. Temp equals temp.next. Is our stack empty? No. We pop it off. Temp.next equals stack.pop, right? Temp equals temp.next. Go to the top. Is our stack empty? Yes. We return new head. So let's try this. Oh my God, and at the end, right, our first, right, so it will be a cycle because 1's.next will still point to 2. So we actually still have to take off that final value that temp is at, do temp.next equals null. So this works, and this would be linear time because we're doing 2 iterations over n basically, where n is the length of the linked list, and the space complexity would be linear space as well, since the stack will have at one point all the nodes that exist within the linked list. So there's 12 minutes left. A linked list can be reversed either iteratively or recursively. Could you implement both? So I guess we reversed it iteratively. Now, could we reverse it recursively? That's interesting. So I think we could reverse this recursively. If we recurse down to the deepest we can get, right, we'll start at 1. We'll say if 1 exists, right, then we'll call a helper and go even deeper. 2 exists, right? So let's call a helper and go even deeper to 4. 4 exists, let's call a helper and go even deeper to 4, right? 4 exists, let's call a helper and go into next, right, which is 5. 5 exists, so let's call a helper, all right, and go into .next. Well, .next is now null, right? So now that it's null, right, now we would be at the deepest point, right? But we wouldn't have access to the front. Be at 5, we want access to so you could say the next, for at 5 we'd pop, right? What if we said 5's dot next was 4, and 4's dot next was 3, 3's dot next was 2, and 2's dot next was 1, 1's dot next was null. I think we could do it recursively, but I think the easiest way to do it, we'd still have access. We'd still need some form of way, you know, to access the other nodes. In that sense, we could do something like where we recurse to 5, we have access. So let's remove our code and keep our edge case, right? And can we do this recursively, right? So what if we call reverse, which will be our helper, and we'll pass in head. And it will return a new head, right? So we'll just return reverse, right? For this function reverse, it'll take a node to be a list node or null, right? And return a list node or null. So now we're in head, right? Which is 1, right? And since head exists, right, we could go all the way to 5, right? And so say if node, right, call reverse of node. Right? So now we're all the way down in 5, right? Because once we get to 5, not the node itself, reverse dot next. So if we reverse the node dot next, maybe if we kept track of both, right, we could have cur and prev, right? And cur and prev could be list nodes or null, right? And we only really care that if the current exists, right? So if the current exists, right, then we want to go as far deep as we can, and so we'll recurse first, right, with node, right, and then not node, cur, right, and prev, which is going to be so when we first call it, we'll call it with head, right, and our previous is going to be null, right, and then we'll go call reverse for 1. If we call reverse for 1, right, cur will be 1 and prev will still be null, then we'll call it. So we're kind of keep going in a circle, right? So maybe the goal would be for not cur, but prev and next. So if we do prev and next, we can kind of reframe it to make sense, right? We really only care that next exists because next is 1, right? And we want to go deeper. So we'll do next dot next, right? And prev is now next. So we call reverse, well, prev is next, right? And next is next, not next. So we call it with null and head, right? One exists, so we call reverse with prev being one and two being next. Then we do it, we say two exists, so now we call a helper with prev being two and next being three. Three exists. Next, prev would be three, next would be four. Four exists, so we call a helper with prev equals four, next equals next, next dot next, right? And then we're at five. Five does exist, right? And reverse, so we say our next, which is five, our next dot next is null, right? So we could have, this could be our else if, right? And if so then, right, we'd go to 5, right? All right, and we'd say 5 is prev, right? But next dot next is null. So we don't do anything, right? Because if next. So then we'd recurse back up, we'd be at 5, right, with access to both 5 and 4. So in that case, we would say next dot next. I actually want to keep, I want to keep a temporary var. We'd say const temp. We'd want to keep, right? So we'd be here in 5, right, with prev being 4 and next being 5. We want to say next 5.next equals 4 and prev.next equals null. So let's try that. We'll say 5.next, right, equals next equals, or next dot next equals previous. So 5 now points to 4, right? We'd recurse back up to 4, right? And with 4 we called previous so if previous exists, then prev.next equals null. And so this does make sense to me. But the node we have at the end is actually 5. So we could iterate to the end and keep that value of, with an array we return won't have the value we want. So let's try it for a short array, 1, 2, 3, right? So 3.next equals null, right? So now we're back, right? With next.next equals prev, right? And if prev, which does exist, prev.next equals null, right? So then we recurse back up, we're at 2, right? With next equals 2 and prev equals 1. So we're going to say next.next equals prev, which equals 1. And if prev exists, which is 1, prev.next equals null, right? Then we recurse back up to 1, right? And next is 1, right? So we'll say next.next, right, which is 1, equals prev, which is null, right? And if prev, I will say prev.next equals null. We don't have to actually worry about prev.next, I think. We can just say prev, next.next equals prev, and prev if we go back to up to 1, right, next would be 1, prev would be null. I think we just want to say next equals prev. So next.next, which would be 1. So let's say we pass, so prev would be 1, next would be 2. Next.next, right, would be 2.next. We want that to point to 1, right? And then next, which is 2. So that doesn't make sense. We have to always working with pointers. I think we want to say that prev.next, which would be 1, equals what? Prev.next. Yeah, I think we were fine with what we had earlier. We'll just say if prev exists, then prev.next. We actually don't need this though. So we're gonna get it in the wrong order. We're almost out of time basically, but I just want to see if we would have reversed but in the wrong order. We have to return a value. We were wrong about that. We're actually gonna just modify the input. We'll return head. It's gonna be in the wrong order, I hope. If it returns in the wrong order, it's actually good. Oops, I'm missing, I kept the semicolon by mistake. Oh, so actually this is good, right? Because 1.next is null. So it's actually good. We just need to find a way to keep a pointer to the end. And maybe what we want to return is that value. So somehow we want to return that last value, which would be 5, which would be the start of the linked list, which is perfect if we're recursing all the way down. The only way to do it would be to return reverse. That doesn't make sense, right? Because we have to recurse all the way down first. So I think one way to do it would just be to create temp equals head, right? And actually go all the way down, right? While temp.next does not equal null, right? We want to stop before we get to the end. We're going to say temp equals temp.next, right? Does not equal null, we're going to go further, and then as soon as it does, that means what we return would actually be temp. So our intuition is correct here. It just took us a little longer than we wanted to get there, so we can reverse it. It's just not in the good time. So now we have a linked list. We like to change it. So they did it with linear time and linear space. This is recursive. Linear time and constant space. Okay. Oh, right. I always forget you can reverse a linked list with constant space. If we keep a pointer to previous. While traversing the list, we can change the current node's next pointer to points to its previous element. Since a node does not reference to its previous node, we must store its previous node, we must store its previous element beforehand. We also need another pointer to store the next node before changing the reference. Do not forget to return the new head at the end. So prev equals null, cur equals head. While cur, we take a temporary value for next, right? Cur dot next equals previous, right? And then previous equals cur. Cur dot next equals previous. let's look at this. Cur dot next equals previous, right? Previous now equals cur. And cur equals next temp. So I think we can do this better next time. The recursive version is slightly trickier, and the key is to work backwards. Assume that the rest of the list has already been reversed. Now how do we reverse the front part? Assume the list n1 goes to m goes to null. Assume from n to k plus 1 so nm had been reversed and we are at node nk. nk plus 1's node to points nk. So nk.next equals nk. N1's next must point to null. If you forget about this, your linked list will have a cycle in it. This bug could be caught if you test your code with a linked list of size 2. So they're doing it like this. If head is null or head arrow next is null, if head is null or head arrow next is null, return head. This node star p equals reverse list head dot next equals head. Head dot next equals head. Interesting. So mine's is a little ghetto in the sense that you had to return, you needed a pointer to the end of the list, right? End of the linked list, and then you could reverse it because we're pretty much abusing how recursion works. But interesting. Honestly, I would still count that. We're able to do both, pretty much the question and follow up in like 25 minutes. I would count that. And so, I think this should be 1. And then we'll reset this one, do 01 matrix. So we have 01 matrix. So we have 01 matrix. Let's see how this is going to work out. So we have given an m by n binary matrix. Mat, return the distance of the nearest 0 for each cell. The distance between two adjacent cells is 1. Okay. So given this binary matrix, return the distance of the nearest 0 for each cell. The distance between two adjacent cells is 1. Of the nearest 0. So the nearest 0 for each cell turn the distance of the nearest 0 for each cell. Oh, so the distance between two adjacent cells is 1. Adjacent means, I guess, left and right only. Oh, the nearest 0. So is this 1 the nearest 0 for this cell? Oh, the nearest 0 for this cell. This is a little confusing. So what is the nearest 0? Example 2, we have 0, 0, 0, 1, 0, 1, 1, 1. The nearest 0, it looks like we only care for cells that already have a 1 in them. Or the nearest 0 for each cell. The nearest adjacent 0 to this cell is none. Nearest adjacent cell is 0. Nearest adjacent cell left to right is 0. Nearest adjacent 0 is 0. And the nearest adjacent 0 for 1 is 1 away. The output be 1, 2, 1. So the nearest adjacent cell for this one would be 2 cells away. I'm not understanding what qualifies as a distance here. I think I have 2 here. We're supposed to have 2 here, but this cell is not 2 cells away from any 0. It'd be 1 cell away. But this one would have 1 because it's Given an m by n binary matrix mat, return the distance of the nearest 0 for each cell. I think it's the clarifying questions here that are getting me. I'm not exactly understanding the problem. We have m, which equals the matrix's length, n, which is equal to the length of the columns for that row. 1 is less than or equal to m. So we know that for both m and n, we'll always have at least 1 row and column in the matrix. 1 is less than or equal to m times n is less than or equal to 10 to the 4. Mats of I of j is either 0 or 1. There's at least 1 0 in mat. So we have to find the nearest 0. So I think I'm starting to understand maybe a little bit. This is 0 because the nearest cell to this is itself, which is already 0. So I guess we only care about non-zero values. If we only care about non-zero values, for 1, the nearest cell that is 0 is 1 square away. The nearest cell that is 0 is 1 square away. Maybe they're also counting diagonals. That's 1 square away, 1 square away, 1 square away, 1 square away. Interesting. So I can't say that I understand the problem 100%. That being said, it looks like we can skip zeros since all the input would be either 0 or 1. 1 indicates that we need to start a depth first search to check the nearby cells. And actually, no. We actually put 2 here, so the nearest adjacent 0 is 2 cells away. So I don't think we're actually checking diagonals. This should be 2 because I think we're only considering up, down, or left, or right. So let's run with that. So to do that, we'll do const row equals 0, row is less than mat.length, row plus plus. And we'll do for const column equals 0, call is less than mat sub row dot length, call plus plus. And then for here, we'll check if mat sub row sub call, right, equals 1, right? Then we want to start a depth first search, right? And it'll just find nearest 0 basically, right? And so we'll set mat sub row sub call equal to find nearest 0, right? We'll pass in mat, the row, and the column. From here, this is going to modify our input, which is fine. And so we're going to have our function, right, find nearest 0. It's going to take a matrix, right, which is going to be an array of arrays, right, but all the values are going to be numbers, right. We're going to take a row. We'll shorten this to R and C, which will be a column, and we're actually going to return a number. So we're going to say distance equals 0, and we're actually going to return distance. But for this depth first search, how could we do this, right? So we start at this 1 here, right? And so we want to check as far up as we can, right? And as far down as we can, as far left as we can, as far right as we can. So as long as these values return 0, right, then maybe it's so actually I see what we can do. We could actually do so it's going to trigger a depth first search, right? We're going to search in 4 directions continuously until we reach our bounds, basically. As soon as we find a 1, we'll just return it, right? And so this find nearest 0 is just going to actually serve as just a place to really call a version. So maybe we could keep going up, then we'll keep going right, keep going left, we'll keep going down. But if you only take an R and a C, then how do you know when you should stop? So you want to keep going in a direction. So let's just imagine this as a process. We'll start at 1, right? I want to say go as far up as you can until you find a 0. Well, we do a depth first search, we check above us, and then we find a 0. This would start another depth first search. So we would say if our call equals 0, right, then that would be perfect. So we'd found our nearest 0, so we want to return that. The thing that I'm stuck on is that's kind of messing me up. Usually you never keep going, so I'm a little uncertain as to the particular mechanism to produce that result. So let's think about it. We're starting at this row and column. We want to go as high as we can and go as far left as we can. So maybe we'll do it like this. Go as high. Well, go far up. Go far right. Go far left. Go far down. Right? And then we could return the math.min of u, which is up, r, l, and d, which would return the minimum distance. Right, so I actually don't think we need distance here. I think what we can actually do is maybe do just a few different functions. So we want to basically declare u equals count, right? We'll pass in mat. We want to go from r, comma, c, right? And we kind of want to go a direction, right? Maybe we'll just pass in a string up, which is definitely not the way we want to do this, but maybe we can get a solution that could work just for right now. And that's really what I'm stuck on. I'm stuck on how to propagate the direction that we want to continuously check in. So if we get a function call, we'll just duplicate find nearest 0, turn it into count. We'll have rc number, right? And we're going to have direction, which is going to be a string, right? And so how do we go about doing this? If we're going up, then we know that we just want to keep adding 1 to row, right, until it doesn't equal 0, right? So if it equals want to return count, right? So what do we want to do? We want to say so we could return count, which is going to go up, and we'll say if dir equals up, right, we'll do C, which is going to modify the input, but it should be fine. We'll do R actually plus equal 1, right, and we're going to have a few more cases for this, right. That besides the case, right, we're going to say if mat sub R, right, sub C equals 0, equals 0, right, then that's a good case, right. We want to return 1. Plus, oh no, you want to stop, right? So as long as if it doesn't equal 1, so we actually want to return 1 plus, so we actually need a way to keep track, and we'll just add a number, right? It's going to be a parameter, which is going to be automatically set to 0. We're just going to say basically return CT, right? And then from here, we'll say we don't have to do an else, right? Else we'll do CT plus 1 plus count, right? Mat R C, and we'll keep going up to dir, right? And so this should stop when it equals 0, or if it equals 0, right? Or if the value doesn't exist, right? Well, actually, if the value doesn't exist, basically we'll know when to stop when we've gone out of bounds. So we'll do an else if, we'll say if R, right, is greater than mat if R is greater than mat.length, right, or R is less than 0, or C is greater than mat sub R dot length, or C is less than 0, right, then we also just want to return CT. This is a mess. This is an absolute mess. Even if we visualize this as a graph, I don't really understand the core of the problem. So I don't exactly know what I'm solving for. I think I have to keep going up. We still need a couple more versions of this. So we have 3 more of these. You go R, L, D, go. We could shorten this R, L, D. So else if dir equals R, right? If it's R, then we want to do C plus equals 1. Else if dir equals L, right? And we want to say L. I mean, if we're going left, we want to say C minus equal 1. And if we're going down, right, then we want to say R minus equal 1. And so let's just run this for now with our first value of 1 here. We'd have 1. Mat sub row sub call equals 1. All right, we're going to find the nearest zero for mat row and call. Find nearest zero, we're going to call count 4 times. We're going to call count with 1, 1, basically. And so with u, right, so we have 1 and 1, right, we're going to say dir equals u, so r plus equals 1, right? So we're actually going to go, up is actually down, so we do plus equal 1, right? We'd go down here, we'd say if mat sub r plus 1, which is 2, which does exist, right, with column 1 equals 0, it does not, right? Since it does not equal 0, no, does it equal 0? It does not, right? So else if, is it out of bounds? It's not. So we're going to do CT, which is 0, plus 1, right, plus count of mat, R, C, and dir. So now we're going to do, we're back in count again, and we're going to say if dir equals u, which it does, r plus equals 1, so now r is actually 3, right? It does not equal 0, right? And r, which is 3, is greater than, is r greater than mat.length? Is 3 greater than 3? All right, so if it's greater than or equal to mat length, then we're out of bounds, right? Because for loops are exclusive at the end. So 3 is greater than, 3 is equal to 3, right? So we're just going to return CT, right, plus oh no, we actually wouldn't return CT. Actually, we would return if CT is greater. Yeah, this solution is all over the place. This solution is all over the place. I'm gonna run it just to see if it even compiles. Duplicate identifier R. Assigned to row, right? Both of these are constants. So we ended up changing so you want to keep looking, right? If we go out of bounds, right? If we go out of bounds, then we just want to return 0, right? But if something equals 0, right, then we want to return CT because that's our closest 0. Otherwise, we'll go CT plus 1 plus count and keep going. So if it equals 1, right, we're going to find the nearest 0 with the row and the column. We find the nearest 0, we're going to call it with U. U equals count mat RCU, right? So we go U. And so we go, if dir equals U, R plus equal 1. Well, we're calling it with 1, 1, right? So dir does equal U, R plus equal 1, right? So we're going to go up. And now I'm realizing I actually want to check for direction afterwards. Because if the node itself equals 0, then that's actually a good thing because we want to return 0. So if the node equals 0 itself, then return the count, which would be 0. Otherwise, dir equals U, R plus equals 1, right? So we're going to go down. Let's actually change this to do what it's supposed to do. To go down, we would actually add 1. And so we're going to go up, we're going to go subtract 1, right? We're going to check if it's still within the range. 1 minus 1 is 0, which is not greater than 3, which is not less than 0, and so on and so forth. Or let's check if C, which is 1, is greater than or equal to 3. 1 is not greater than or equal to 3, and 1 is not less than 0. So we're going to return CT plus 1, which is 0 plus 1 plus count, right? And we're going to go up. We're going to say, okay, we're back at RC, right, which is now 0, right? We're at 0, 1. If dir equals 0, we're going to do, right? And it does equal 0, so we're going to return count, which should be 1. So for that 1, we should get 1. But if we're going to take the min of all of these, you get 1, 1, 1, and we get 0 for this. We shouldn't, because let's check if we go down. We do R plus equals 1, right? So now we're going to call it for count. We're going to be at row equals 2. 2 is not greater than or equal to 3, right? So we go into it, right? We're going to have count plus 1, right? 0 plus 1 plus count, right? So does 2 sub 1 equal 0? No, right? Let me look at this one more time. We're going to go down. We're going to go down. So RC, we're going to start at 1, 1, right? Is 1, 1 equal to 0? No, it's not, right? So we do dir equals down, so we do R plus equals 1. So now R is now 2. We're still in the range, so we do turn CT plus 1 plus count. R equals 2, column equals 1. So does 2, 1 equal 0? No. I think I'm seeing my problem. If Now we're going to subtract it. And we actually don't, if we go out of bounds, we don't actually want to return 0. We want to return count. Okay, so we're looking good. So something is not exactly working out. For this version, we have 0, 0, 0, 1, 0, 1, 1, 1. We returned for this 1 at the end here, we should have returned 1, but we didn't. So let's check what happens when we go left, right? We're at this 1, we're going to go left, right? So we're at 0, 1, 2, right? With 0, 1, 2, right? We're at 2, 0, right? Does 2, 0 equal 0? No, right? But dir does equal L, so we're going to do C minus equals 1, right? So now we're going to be at 2, negative 1, and column, is column greater than or equal to the length? No, is column less than 0? It is, so we're going to return CT, right? But that actually gives us the wrong value. We want to return CT plus 1 because we still went left once. Actually, I didn't get to copy the test case I failed, but I'm pretty sure it's this one. So now we're getting 1s, but for this secondary here right now with 2, so we start at 1, right? And we should go all the way up here, right? So let's check what happens when we go up. When we go up, right, we start at 2, 1, right? Does 2, 1 equal 0? No. I think I'm already seeing the problem. We always want to return CT plus 1, basically. No, I started just guessing. So does 2, 1 equal 0? No. We want to go up, right? So we're going to do r minus equal 1. So now we're going to be at 1, 1. Right? We're going to say, are we in bounds? We're still in bounds. So we're going to do CT, right, plus 1, which is now 1, right, plus count of R, C, and dir. Right, so we're at count equals 1, right, and we're at count equals 1, and we're going up. So we're at 1, 1. We're going to say, hey, does 1, 1 equal 0? No. We want to go up still, so we're going to go to 0. Is 0 out of bounds? No. So we're going to do CT plus equals 1 plus count, right, with 0 and 1. So we go up to 0, we're going to say, hey, does mat sub R sub C equal 0? Yes, so we should return 2. I see, but we're taking the min. I think we are actually getting the correct value, but we're taking the min. If we go out of bounds, I don't think we want to return CT plus 1. It doesn't mean we actually found a 0. What we want to return is negative infinity. We want to return is infinity, actually. So for this quite massive input, nearest zero, the nearest zero to this zero is 1 away. But for some reason we have 2. Interesting. So for, it's like we're slightly off. We're having like an off by 1 occasionally. So for this 1, the closest 0, the expected was, closest 0 was 2 away. But it's not. It's 1. We got the right answer anyway. Maybe adjacent only means left and right. If we run with that rule, adjacent only means left and right. What's the closest 0 to this? It's itself. So we have a 1, right? What's the closest 0 to this 1? Should be 1. What about this one? The closest 0 to this 1 is this 1. The closest 0 to this 1 should be 1. I output 2. They also output 2. So maybe it's 2 steps to the side. It is. If we go 2 steps to the side, so let's actually remove up and down. I think this is actually only supposed to be done for L and R. If that's the case, it does simplify the logic a lot. Let's try RI and L. So for this version, if we only check left and right, then the closest 1, the closest 0 is just not. Are you supposed to check diagonals as well? It's just unclear. The problem is just very unclear. Maybe we're supposed to also check diagonals. So let's try also checking diagonals. And then we'll also have a upright, also have a down right, of a down right. We'll also have a down left, and since we have a down left, right, we'll have an up left as well, and we'll just add these 4 new upright, down right, down left, well, upright, down right, down left, up left, right, down left, up left, down right, up right. Let's just check all around it. Maybe that's what they mean. And actually, we could actually reuse these if we just say if dir includes R, right? If dir includes, actually no, we can't do that. So we just need to handle basically all these cases. So we have right, right, down right, which is going to be C plus equals 1 with row plus equal 1, right? And then we're going to have right, down right, and we're going to have down. Down is just R plus equals 1. Then we're going to have down left. Down left is just down, right, which is R plus equal 1, and C minus equal 1, and then left is just C minus equal 1. Up left is just C minus equals 1 and R minus equals 1, and then I think we're just missing up. So 1, 2, 3, 4, 5, 6 should be 8 directions. 1, 2, 3, 4, 5, 6. We're missing 2. We have up left, up. We have up. We're missing up. So we'll do else if dir equals up. And then up is just R minus equal 1. Right, so we have up, down, left, and right. We have down right, down left, up left. So we're missing up right. Upright. To upright, you would do minus equal 1 and C plus equal 1. Leave this extra character. Let's try this again. Up is minus equal 1, which makes sense. Left is C minus equals 1. Down is R plus equal 1. Right is C plus equal 1. Down right, we add 1 and go down 1. Down left, to go down left, we would add 1 and subtract 1. To go left, we just subtract 1 left. To go up left, we would subtract 1 from the row in the column. For dir equals up, we just subtract 1. And for upright, we would subtract 1 from row. But we can't include diagonals because if that was the case, this would turn into 1. But no, it's 2. I think I'm gonna be honest. I think the problem. I just don't get the problem. I thought I understood the examples, but I don't know what adjacent means. Distance between two adjacent cells. Return the distance of the nearest 0 for each cell. Maybe we just toss out all this upright, downright, DL, up. Nonsense. We toss that all out the window. So what if we remove all this nonsense, right? And maybe it's for every cell regardless. If that's the case, let's just do this. So we're not even close. Yeah, this is just an interesting problem because I think if someone was asking me the questions, I could figure out exactly what I'm supposed to do. I'm looking at the output and exactly why this isn't working, and I'm just not understanding. So our output says 0, 0, 1, 0, 1, 1, 1, 1, and for some reason we're producing 2 right here. So we're producing 2 because for this particular one, the closest 0 should be below it. For some reason we're returning. Oh no, they actually get 2 as well. So the closest 0 is not even below it. So I honestly don't know what they're checking for. The closest 0 to this cell is 1. The distance of the nearest 0 for each cell. I feel so close. I just don't understand the problem. This is our input. Oh, oh my God, I think I see what's happening. The rows are actually wrapping. And it should actually be something like, oh man, this is why I don't understand why the output is wrong. Because my rows, I assumed that this was in the perfect grid formation already. So it just seems that we have a long one here. Wow, this is taking a while. It might just be faster if I use my mouse. And so my output is this. I really wish they would have auto-spaced this for me. Like, and so I actually should just did this with my output and their output to see what truly the difference was. Okay, so there's a difference between our output. The first row looks fine. Second row is just all wrong. Oh my god, I think I might have figured out the problem. If you change the rows, I never actually, no. I am modifying the rows. Maybe that's the problem. Modifying the rows, maybe they want to operate on a non, so if we just copied it, say const copy equals mat. So we get all the arrays, the initial arrays. I'd say we just copy it like this. Maybe we could do, and we'll say equals this, and we'll say r.push mat sub call, row sub call, right? And then outside of this for loop, we'll just say copy dot push r. And that way we'll have a copy, and so what we're working on, right, is always the clean version. So the version that we're going to be modifying, we can do something like this, where we only ever modify the copy, and we're always looking in the good version. And that way we could return copy, but not modify mat. Well, that actually doesn't make sense because our first version worked. Yeah, I don't think this is going to work. So our first version worked while modifying it. Remember, that was a coincidence. So it still works. And it's still incorrect. We're just going to read the solution. Let's start with the most intuitive approach and do exactly what the question asks us to do. For each cell, find the distance of the closest zero. Initialize this sub I sub j equals int max for all I j cells. Iterate over the matrix. If cell is 0, dis sub I sub j equals 0. Otherwise, for each one cell, iterate over the entire matrix. If the cell is 0, calculate its distance from the current cell as the absolute value of k minus 1 plus abs of L minus j. The distance is smaller than the current distance, update it. The brute force method. Better brute force, looking over the entire matrix appears wasteful, and hence use breadth first search, limit the search to the nearest 0 found for each one. As soon as a 0 appears during BFS, we know that the 0 is the closest, and hence we move to the next 1. Think again, but in this approach we only be able to update the distance of 1, 1 using 1 BFS, which could in fact result in slightly higher complexity than the brute force approach. But hey, this could be optimized if we start the breadth first search from zeros, and thereby updating the distance of all the ones in the path. Q to maintain the queue of the cells to be examined next. Start by adding all the cells with zeros to Q. Initially, distance for each 0 cell is 0. Distance for each one is int max, which is updated during the BFS. Pop the cell from the queue. Examine its neighbors. If the new calculate distance for a neighbor is smaller. Int rows equal matrix dot size. They're doing their own update update matrix. So yeah, there's just a lot of silly mistakes made. We are supposed to update the matrix. And adjacent means up or down or left or right. So when we have to do that, one way to automate it is to just iterate over pretty much the changes we'd like to make to the rows and the columns. Cur dot first plus dir sub I sub 0. Oh no. They're doing this iteratively. This is pretty much an iterative. Looks like they're doing a level order. No, not even a level order version of this. It looks like they're just checking it looks like they're literally checking nearby. But if that's the case, how is it that this 1 becomes a 2? Because the nearest 0 here, if we're only checking up and down, the nearest 0 does not exist. Nearest 0 for each cell. The nearest 0 is 1 away, and they're adding 1 to this 2. Yeah, that's where I messed up. They're adding it. At the same time, you didn't have to keep checking. You just had to literally check the ones surrounding it. So I think the one where we check up, right, down, left was fine. You just didn't need to calculate it in all 4 directions. So if let's to see if we really understand it. Let's check. We could do. Wait, no, that doesn't make sense because if we look here, they only have 4 that you can actually check. Dir. It's only checking left. Unless you can wrap around. What if we just stop this propagation nonsense and just do a regular count? So that we could remove this weird copy thing we did, change this to mat, and we'll just call it find nearest 0, where we call count for we'll fuse then let's just check basically nearby. I do DFS for it. If we change it to only look at nearby, add the value to it, could we do that? So we have count and find nearest 0. What's the difference here? We're just trying to return the math.min of that. That being the case, this doesn't even have to be recursive since we're just checking nearby. And so we could just return 1. Not even a point for CT, because if it equals 0, we just return 0. If it's out of bounds, we just return infinity. Otherwise, we return 1. And so to check all around us, we could just do, to check up, we do r minus 1. To do right, we would do column plus 1. To do left, we do column minus 1. To do down, we do column, we do row plus 1. Then we could check the surrounding directions. We'll call this upright, downright. No, we're not supposed to check the surrounding directions, but I also don't see how it makes sense any other way. So we don't even get the right answer. Let's go back to our previous where we only do this if we run into row and column equals 1. let's say we're just guessing at this point, and we're supposed to add it to the value itself. So we're supposed to say we're not supposed to add it. Yeah, I think in the end, I think I just don't get the problem. I don't really understand what they're asking me to do. I really don't understand. I think we're just guessing at this point, to be honest. We've been long out of time, but yeah, this one, I don't get it. I do not understand. A better brute force. Looking over the entire matrix appears wasteful. And hence, we can use breadth first search to limit the search to the nearest zero found for each one. As soon as a zero appears during the breadth first search, we know that the zero is the closest, and hence we move to the next one. Think again. But in this approach, we will only be able to update the distance of 1, 1 using BFS, which could in fact result in slightly higher complexity than the brute force approach. Okay, this could be optimized if we start the BFS from zeros and thereby updating the distances of all ones in the path. For our BFS routine, we keep a Q to maintain the queue of cells to be examined next. Start by adding all the cells with zeros to the queue. Initially, distance for each zero cell is 0, and distance for each one is int max, which is updated during the BFS. So rows is equal to matrix.size, rows equals 0, return matrix. Calls equals matrix sub 0 dot size. So here we have, they're pretty much creating a new matrix, right, called dist with rows, and it's going to have rows with calls, and the default values are going to be int max. Then we iterate over I is less than rows, I is less than calls, and if matrix for this copy, if the original value was set to 0, then we'll set this new one equal to 0 and push it as a queue, as a cell to examine. Okay. While the queue isn't empty, we have all the zeros we want to examine. Pair int, right? We have q dot front, which is going to be the row and the column. So for the first one, right, we're going to be having this 0 here. And then we're going to say for an I equals 0, I is less than 4. New R equals cur dot first, which is 0, plus dir sub I, which is 0, is -1, and new C, which is cur sub second, is I, which is 0. So we're going backwards first. It's out of bounds, so we ignore it. Then we finally have one that's inbound, so we check the next index over. We are inbounds. We're going to say if dist sub new R, which is 1, sub new C, which is 0, is greater than dist of cur dot first. Cur dot first is the original row and column plus 1. I think I just realized why this doesn't work. So our code doesn't even work with the basic output anymore. I'm not even sure what we did to it to do that. We set it equal to 0. Let's set it back equal to 1. I think the solution might be that we didn't account for the fact that the mats of row call is smaller than the one we find. You guys done?
Are you done?
Yeah, are you guys done?
Oh yeah, we're done for the night.
So if we run it like this,